We've talked about figuring out if your truss is statically determinate, if we can even solve a problem. We've practiced external forces where we use moments, X forces, and Y forces to see how big your reaction forces must be to maintain static equilibrium. Now, the last step we need to take is internal forces, where we really dig into each individual member of your truss to figure out how much force it's providing to maintain that overall static equilibrium. And the way we're going to do that is a system that we call the method of joints. And this is just a process that we're going to use to make sure that our calculations turn out and we can figure out what direction a force is acting on a member. So there's a few steps that we're going to do. Number one is we're going to assume that all members are in tension. And that's kind of why we erase the middle part of our trusses and show that the arrows are kind of going away from our joints. We're going to use sine and cosine, those vector components, to figure out the forces in the X and the Y directions. And then as we solve each individual force, that's going to give us clues to solve other joints as we kind of work our way around the truss. So again, it's a big problem-solving exercise, and there's a lot of different ways to solve this, but we're going to give you kind of a framework or a skeleton so you can solve these problems. Now, before we dive into an example, one really important thing that you need to think about is the direction of your forces. Now, in terms of X and Y, we define positive as right for the X and up for the Y. We defined a clockwise rotation as a negative moment. When we find positive and negative values within a truss, we're talking about tension and compression. So when we have an object in tension, we're focusing on a joint. So if we have members pulling at the joint, we're considering that member in tension. And if we have forces pushing onto the joint, we're going to call that a compression force. So to start off, we're going to assume that everything is in tension. And if we find there's a negative value, then we know that it must be in compression. So if our guess is wrong, if we guess tension and it comes out negative, we're going to flip it and call it compression. And we're just going to start changing things as we go through the process. So let's dig into the last part of our truss solve, internal forces. All right, we finally made it. The last step in our full truss solve, which is to find the internal forces using the method of joints. So what I'm going to do is I'm going to use the example that we pulled from in the external forces video, and we're just going to finish that off since we already have that work ready to go. So you should have the truss solving template with the external forces ready. I clipped it out just so I can zoom into the image for you so you can see my terrible handwriting. But you'll definitely need to flip back and forth between those two as we are solving for internal forces. Now, the reason why we erased the middle of each of those members was because we're always assuming that all of our forces are in tension to start off with. So if we have A, B, C, D, if we are in tension, what it means is the member is pulling away from your joint. So force from A to B is pulling away, it's stretching it out. If we were to flip this guy and go the other way, that member is pushing on or compressing the joint. So when we say compression and tension, we're talking about what is happening to the joint that it's attached to. So notice how the force from A to B is pulling on joint A. It's also pulling on joint B, so those are both in tension. So we can't really think about it as a specific direction. We want to think about it as, is it pulling your joint, like stretching it out, or is it compressing it and smushing it down? So this is assuming that everything is in tension, all set up and ready to go for us. And if we find a negative number, we just know that it should be in compression, and we'll just flip it to go the other way. So according to our truss solving template, we need to look at each of these force diagrams individually. So we have joint A, joint B, joint C, and joint D. So we need to make some decisions on where do we need to start. And there's a lot of different ways you can solve for this. Some ways are going to be easier than others. What I like to do is I love knowing things and I hate angles. So if I look at joint A, I know the y direction force, I know the x direction force. I do have a couple of forces I don't quite know here, but that's not that big of a deal. I love this force diagram here because we're purely in the y and the x, but I only know the y, which is going to be a pain in the butt. I can look at D right here. I know one of these. That might be a good one to start off with too. I'm going to avoid B as much as I can because I don't want to break down two of those forces using trig. So we're going to have to break down these vectors like we did in one of the earlier videos. So I'm feeling, I don't know, let's start with joint D over here. So what I'm going to do is I'm going to take this force diagram and I'm just going to draw it up in this spot. So I'm going to focus on joint D to start off with, just because it looks like I can actually solve for some junk. Let's see, RDY, and I'm literally just copying and pasting that thing in there. 637.5. What we also have going on is a force from D to C. So I'm going to call that, wait for it, very clever, FDC, which means the force going from joint D to joint C. And we also have the force going from D to B, which is that angled guy right there. So FDB, whatever that ends up being. So again, I'm just focusing on this and ignoring all of that other junk. And I know my angle in there is 56.31. So notice how FDB is angled. And if we think back in our vector component video, we need to break that thing down. So the sense of that angle is there's a piece of it that's going to the left, and I'm going to call that FDBX, so the portion of FDB in the x direction. And FDB is also going up, so I'm going to call that FDBY. And we solved for that angle in an earlier video. So I'm just going to write that over here in case we got to deal with trig, which, spoiler alert, we're definitely going to have to do that. Okay. Now we're going to work on this much like we did for the external forces, except we're only dealing with forces in the x and forces in the y. So we don't need moments anymore. So let's think about our process. How do we need to solve this thing? As I look at it, I have two forces going in the x, FDBX and FDC. I don't know either of those, so it's probably not a good idea to start there. Excuse me. But I do know RDY in the y, and my only other y force is FDBY. So that might be a good place to start. Notice how I'm not really solving for FDB quite yet, but that's going to help us solve it. Now, there's a couple of different ways to solve for these things. If you want to find FDBY and then take another step to use your angle, your opposite side to find FDB, you can totally do that, but for sake of brevity, assuming that you already know how to do this, I'm going to go through a quick little shortcut to solve for FDB. So let's get into it. In the y direction, RDY is a positive value, so I'm going to keep that as positive. The way that I drew it based on that sense, assuming everything is in tension, FDBY is also positive. And those have to be equal to 0 in order to maintain that static equilibrium. Okay, so let's break this down just a little bit. If we want to toss in RDY, we definitely could. 637.5 plus. Now, I want to break this down into a trig function because ultimately my goal is to find FDB. We could use FDBY to solve for it, but my overall goal is to find what that angled force is. So I'm going to say FDB, just like we did before. If I were to solve for that, because we have the opposite side and we're looking for that hypotenuse, I'm going to be using sine of my angle, which is 56.31 equals 0. So notice how I just kind of went, this is my hypotenuse. To find the y, in this case, I'm going to do sine of that angle. And if you are not quite sure how to do that, or if you need to take some time, feel free to pause the video. If you need to go back to see the other tension, or excuse me, not tension, but trig video, you can definitely do that too. So let's go ahead and solve it out. So we have FDB. I'm going to subtract 637.5 to the other side. FDB sine 56.31 is equal to negative 637.5. And then my last step would be to divide everything by sine 56.31 over sine 56.31, and then use my fancy calculator to figure that out, because I know it sounds crazy, but I can't do that in my head. So I come up with FDB is equal to a negative 766.1, and I'm going to round 0.18 pounds. Now we've got a little bit of an issue. This guy came out negative. So our initial guess was not correct, which means that this guy is not in tension, it's in compression. So this should actually be kind of squeezing our joint. So we've got to flip it. And this is going to be kind of a pain in the butt, because by flipping that hypotenuse, it also messes with our x on our y direction. So instead of having our arrow going up like that, it's going to be compressing, pushing on our joint, which means that the sense is different. So my sense is now down and to the right. Instead of left and up, it's down and to the right. Okay, so we found FDB, 766.18, and that is in compression, so maybe I'll just put a little C for later on. All right, hey, that's pretty good. Now, if I look at my force diagram, I've got RDY. I know FDB, which means I can find FDBY, FDBX. Let's find FDC and keep moving from there. So I'm going to focus on all of the forces in the x direction. So the way that I drew it here, we have FDC is going to the left, which means it's a negative value, FDC. And my FDBX, the new sense is going to the right, which is positive. So FDBX, the x component of FDB is a positive value. Okay. Hey, not too shabby. So let's keep going from there. I don't know what FDC is quite yet, but I can break down FDBX into FDB. This time I'm using the adjacent side in my hypotenuse, so that would be cosine of my angle. So let's plug in our numbers. Negative FDC plus, I figured out FDB was 766.18 times cosine theta, 56.31, equals 0. And I'm actually going to add FDC to the other side, just to make things nice and positive. So if I add FDC to both sides, I get something that looks like this. And if I use my handy dandy calculator, 7066.18 times cosine 56.31, beautiful. I find that FDC is equal to 424.999. We're going to say that thing is 425 pounds. And because it came out to be positive, I know that my guess is right, which means we're going to keep that bad boy in tension. Beautiful. Okay. Whew, I'm tired already. Oh my lordy. Okay. So now let's kind of reevaluate. We solved for everything we could around joint D. Now let's figure out where to go from there. So we actually found out FDC. So we found out the whole force right here. So we actually know this guy right here, which is kind of nice. We also know FDB, but again, I don't want to deal with all that trig. So maybe for our second one, let's focus on the forces around joint C, because I think we'll find that a little bit easier than going about joint B. Great, so let's take joint C, and we're just going to draw that into our truss solving template. So free body diagram for joint C, and I'm just going to use what we found in the external forces shenanigans. So we have the force on C was 600 pounds. We've got force of, what is that, CB equals something, we're not quite sure what. We've got a force going to the left, which is FCA. And the force from C to D, we found earlier that guy is still in tension, so our initial drawing still works out, luckily for that one. So FCD, and that's something we already know because we saw for DC, and since they're the same member, they're going to be the same value. Sweet. Okay, I think we're going to find that this calculation is going to be quite a bit easier because we don't have to deal with any trig. Let's, I don't know, let's start out with the x direction stuff. So we are given FCD is a positive value because it's going to the right in the x direction. FCA is a negative value because it's going to the left in the x direction, which makes our life so much easier because we know those two have to be equal to each other. Whoops. And of course I mess up on writing the value, saying how easy this is. So we know that FCA has to be 425 pounds. And since that turned out to be positive, we know that guy's in tension. Beautiful. So let's record that onto our force diagram. We know that guy's in tension. I guess we know that guy's in tension too. So let's go to our y direction shenanigans. So we have FCB, which is positive because it's pointing up, minus FC because it's pointing down. And we're going to find the exact same thing. This is going to be nice and easy. FCB, I'm going to skip a step. Since we know that FC is 600, if I add 600 to both sides, I know that FCB has to be 600 pounds. And because it turned out to be positive, we know that guy's in tension as well. So it looks like we found one in compression so far, and the rest have been in tension. Whew, okay, I like that joint a lot. That was nice and easy. Let's keep that up. So we've finished joint D. We finished joint C. Now we have a decision to make. And honestly, it doesn't matter either way, but I don't want to deal with trig. So we have to mess with two broken down forces here. We know this force, we know this force, we know this force. So I guess there's one unknown. For joint A, we know this force, this force, this force, and we have one unknown. I'm feeling joint A right now, just because I want to avoid doing multiple pieces of trig. Let's just jump to that. So I'm going to jump into joint A, and I'm going to copy that joint into our area for the force diagram. So we know good old Ray, we solved in an earlier video to be 37.5 pounds. We found Rax to be 500 pounds. We found FAC is equal to FCA, since it's just the same old member. So FAC and FCA are the same thing, which means that is 425 pounds. We already know that guy's in tension, so that remains for this one. The only thing we don't know is that stinking angle force, which is FAB, and we need to break that down. We need to find its sense, which is right and up. So this is FABX, FABY. And in the external forces video, we found our angle there to be 26.57. Okay, there's a lot of information right there. So let's check it out. We need to figure out FAB somehow. So we need to find either FABX or FABY. Here's what I'm feeling. We've got 1, 2, 3 X forces and 1, 2 Y. Let's just save us a little bit of a headache and jump to the Y because we have less forces to deal with. So FABY is positive because it's going up in the Y direction. Ray, the reaction force on joint A in the Y direction, is negative. It's going down. So I'm going to write that as negative. And that's going to equal 0. Hey, this is kind of nice. So let's break this down with our trig function. So FAB, which is our hypotenuse. If we were to solve for that, we have the opposite side. We have the hypotenuse. So I would want to use sine of our angle. And let's just add ray to the other side just to make it pretty in the end. And then we can start plugging some numbers in there. So we have FAB, which is the thing that we're really solving for, times the sine of 26.57 degrees equals ray, which is 37.5 pounds. So let's divide everything by sine of 26.57. Sine of 26.57. And using my handy dandy calculator. Hold on. We find that FAB is equal to 83.84 pounds. Because it is positive, we know that that guy is in tension. So we have 83.84 pounds in tension. Okay, cool. Let's think about this. I know everything. I know this force, and this force, and this force, and this force. If I look at this member, I solve for FAB, which means I know this whole member. Hey, we solve for everything. We don't even have to touch joint B because we already solved for the other forces that are connected there. So we don't even have to do that last part. Sweet. Oh, that makes me so happy. Whew, man, this was a heck of a process. But there's one last thing. We need to finalize that answer. We need to identify what does our final solved truss look like. So what we're going to do is we're going to redraw one more time, I promise. And we're going to identify every single force that we worked so stinking hard to calculate. So I've got my handy dandy ruler, making sure all of my members are straight. Let's see, we solved for ray already. So we've got 37.5 pounds. We solved for RAX, which was 500 pounds. Let's see, we solved for FAB. Where is that thing? Oh, that was the last thing we solved for. What's wrong with me? So we write 83.84 pounds. And we're going to identify that it's in tension. So talked about this member right here. Let's see, FBC. Where is that guy? Here we go. FCB is 600 pounds. Wait, what's wrong with me? Did I mess that up? Sorry, I picked the wrong one. FDC is 425 pounds. Holy smokes. That would have been bad if we just tripped at the finish line. And that guy was in tension. FDE DB, which is our big old angly guy right there, we found to be 766.18 pounds, and we found it to be in compression. We found our reaction force over here was what, 637.5 pounds. Let's see, we found that really long force to be, what is that, FAB, which was 83.84 pounds in tension. And last but not least is that vertical guy, which was FCB, the thing I was originally trying to put down, as 600 pounds. So let's, I'm just going to turn this the other way. Boom. Holy smokes. So really, we have finished our first entire truss solve, and it's a long process, a lot of places to mess up, but make sure you are being super careful with setting up your equations, making sure your directions are right, and as long as you set that up properly, the answers will always tell you if you are in tension or if you're in compression. And if you find that it is in compression, make sure that you switch your direction so it doesn't mess up your future calculations. Whew! I'm going to go take a nap.